Okay, hey everybody, I'm Brett, your instructor for Earth Science. I am sorry, this is the quickest I could get to this particular type of lecturing. With the other class I got handed late, not only do I have to make all the slides, I have to record over them. So that's why I missed the first several chapters. I apologize. Hopefully I can keep up with all this as we go forward. I'm hoping these will help you a little bit so you're not just reading the book. Um, my background is in geology. So if you don't know that already, I'm Brett Ketter. My bachelor's degree is from University of Wisconsin Milwaukee, which is where I work my day job. Um, and I graduated from that department in 1996, and then I went off to St. Louis University and have a master's degree in seismology or earthquakes um, from St. Louis University, which I got and graduated in '99. So I've been at UWM for since 2001, and I've been teaching at MATC now for 5 or 6 years. I can't even remember. Mostly GIS, but I think that got canceled. This is the third time I've done earth science, and every time I got the last two times I got this class, they handed it to me literally within a week of it starting. So I never got around to doing these types of lectures. And then with COVID and everything, I just figured now is the time. I will do my best to keep up. So now I'm basically doing two of these a week. I already did all my GIS stuff over the summer for my other class, so I don't have to record those. So let's get going. I'm gonna have to review some of this stuff as I go. I haven't seen some of this stuff for a while, but let's look at matter and minerals. Okay, what's the definition of a mineral? Well, it's a natural substance found in the earth or in the universe, I guess. It's inorganic, it's a solid, and it has a orderly internal structure of atoms. What that means is, and it has a definite chemical composition. So, what does that mean? Well, I always ask kids when I do school groups, I said, what's the difference between a rock and a mineral? Okay, so a rock is any naturally occurring solid mass that contains minerals. So I always use the cookie analogy, right? Because we all like cookies of some sort. At least I hope you do. So if I'm making chocolate chip cookies, right, I like to eat the cookies. The cookie's the end product. But what goes into making that cookie? You have chocolate chips, right? Or whatever you're going to put in there. You have flour, sugar, pinch of salt, right? All these ingredients that go in there. The ingredients that make the cookie are the minerals, and the cookie itself is the rock. It's made up of all the ingredients. Then you add, temperature and pressure and everything. So that's the analogy I always use. So minerals are things like quartz or feldspar, fluorite. Um, the- some minerals are also elements, which we'll get to in a bit. Things, if you've ever seen a periodic table of elements, things like lead or silver, gold, those are both elements and minerals. Now, when you combine minerals together, you get rocks, which will be the next chapter. A rock is like granite, right? Red granite is the state rock. It's Wisconsin state rock, and it's made up of mostly pink plagioclase feldspar, quartz, and mica, which is muscovite or biotite. The flaky dark black mineral. So those three are the main ingredients that make up granite. So the ingredients are the minerals: quartz, feldspar, and muscovite. So those are the ingredients that make up the rock. So here's some examples, and I know my face is covering the one down, and this is exactly what I just said, right? I should have previewed this first. Um, so you have granite sitting there right there in the middle on the top. That is the rock. It's made up of three ingredients: quartz, hornblende, sometimes it's mica. This particular one is hornblende, and feldspar, which I'm covering, the pinkish one. So those three minerals, the three minerals at the bottom, are combined together to create a rock. Now, can't talk about minerals without going smaller. What are atoms? Atoms are the building blocks of, well, everything, but in this case, they're the smallest particles that you can have that make up minerals. So when I say quartz, what is quartz made of? Well, it's made of silica and oxygen, all right? That's why we call it a silicate mineral. Silicon is one type of atom, and oxygen is the other type of atom, and then they combine in such a way that creates quartz or silica. All right, so all your little sand grains, regular sand, not like black sand or anything like that, but your pretty much normal sand grains are made up of silica. That's why they use it for glass. So when you're looking at atoms, you have the nucleus, which is the smallest, the real small part in the middle, which contains the protons or the positively electrical charges, and neutrons are the neutral ones. And then you have orbiting outside this, middle section, you have the electron shells that contain the electrons of various numbers, various levels. And again, we're not going to go into the deep chemistry of this, but each atom contains those three pieces, so to speak. So here you can see you have the let me grab a marker here. And here you have the nucleus, this little ball in the middle, and orbiting around that nucleus is the electrons. Now, in a perfect world, you have exactly one neutron for every proton, right? So they balance each other out, and then a certain number of electrons going around it. All right. Now, in reality, it's more like an electron cloud than an orbit, but it's easier to visualize with these sort of rings that go around the nucleus. So that's kind of how we look at it, but it's more like a cloud if you were to look at it in almost in 3D. It's almost like a ball cloud. Um, but what happens is sometimes you'll get things like, well, you'll lose a neutron and then it becomes more positive, or you'll lose an electron, and that happens with things like radioactivity, or with when you're smashing. You have spontaneous energy being emitted, things like that. And we're not going to go into all that, but the point is just understand that in a perfect world, the number of neutrons and number of electrons equals each other, and that's what makes up that particular element. So the atomic number is the number of protons. So if you look at a periodic table, all right, you have the simplest of all the elements is hydrogen. It's number one. It has one proton. That's it. One proton, one neutron, and and one electron. So you you have this very basic structure of hydrogen, and then you go to number two, which is helium, which has two protons, and then you go from there. Okay, number three is calcium, so you jump from a gas to a solid. So um, and then you have ions are positively or negatively charged atoms due to the number of electrons that are either gained or lost. All right. So just because you have one type of element doesn't mean that's the only type of element. There are sometimes other versions of it. For example, just to use an example, the oxygen we breathe every day is O2. It has two oxygens. They're combined together. Ozone, which is in the atmosphere and also created by pollution, is O3. So it's still oxygen. It's just a different form of it. All right, that's just one example. When you start getting into the radioactive minerals, you have what are called isotopes and things like that. And that's where you have more or less of something, but it's still like uranium. There's different kinds of uranium. They use uranium 238 for most things, but there's also other types of uranium that might be either less or even more highly radioactive. So we know that these atoms are the building blocks of everything in the universe, right? And there's over 100 of them that are known. See, when I was in school, it all went up to 103. Now I think they're up to like 120, maybe. I haven't seen one, and it's defined by the number of protons. So where they sit in the periodic table is where the number of protons. That periodic table, if you don't know this, is absolutely the coolest thing ever. There's so much information as to why all of those elements are grouped the way they are. Even if you're not a chemistry person, it's just an interesting. I found some. It's interesting to know what the elements are, when they were discovered, what they're used for. And there's YouTube videos that'll take one element and explain to you, you know, what this stuff is used for. You'd be surprised at how many things, especially like your phone. Your phone has all these weird elements in it, and that's why they want people to recycle them, because those elements cost a lot of money because they're rare, what they call rare elements, even like platinum and things like that. So yeah, it's interesting what all this stuff is used for. So here it is. So you have this periodic table of elements, and I'm not going to go into huge detail on this, but small side stories. When I was in chemistry in college, I was lost. I really had a hard time. I'm not going to lie. But what I did do is I memorized this thing. I still know pretty much what every element on there stands for. If you just give me the symbol, I just memorized this thing just for because I was bored. I probably shouldn't tell you that. But so it's really interesting again to see where things sit. For example, just let me give you a quick example. This, oh, I had that wrong. Lithium is number 3. I apologize. I said calcium before. I don't know why I said that. So that first column right there are called the actinides. Actinides? I forget. What's really neat about those is they are highly, and I mean highly reactive with water. And you could see videos, especially with like cesium, which is down here. This is cesium. They'll take this tiny little chunk of cesium and throw it into like a pool of water, and the whole thing just blows up. It's really neat. So chemistry can be fun as long as you don't have to worry about all the dirty details. But chemistry is really interesting as to what things are used for, and like I said, who discovered it, when it was discovered, what it's really interesting this whole table, as long as you don't have to be tested on it. So the atoms are bound together. Okay, I'm not going to go into all this. I don't even think you're tested on a lot of this stuff. But I wanted to touch on some of this. You have you need 8 electron shells. The shells are sort of the layers that come out from the nucleus with the and they have these bonds that come and go in terms of making sure that essentially everything stays balanced. Once things become unbalanced, then you have what are called like reactions, and that's not necessarily what you want. So we have these things called ionic bonds, which are basically um, where you have like if you have a perfect balance of positive and negative. So they use sodium and chlorine, right? Sodium and chlorine is a +1 -1. They combine very nicely because they're completely opposite, and you get sodium chloride, which is salt. That's all that is. Sodium chloride is what you put on your French fries. You shake on your French fries. So the idea is you have sort of the same amount of negative and positive polarity, and they attract to each other. Now, let me give you a little example. If you have two magnets, just little bar magnets, okay? And if you put the positive and positive or negative and negative, and you try to put them together, they won't. They won't go together. But if you take them and you flip one of them on the other way, all of a sudden they snap together, right? They need that opposite charge in order for it to work. So this is a perfect example. You have a sodium and a sodium is a +1, chlorine is a -1. Then they attract perfectly and create table salt. So a covalent bond is sharing of electrons between two uh, atoms. And this gets a little bit more complicated. So you have a hydrogen atom and then you have another hydrogen atom because they're both -1, they seem to actually work well together, and they won't stick to each other necessarily in that sense. But what they do is they're oppositely charged. So, but they have the positivity in the nucleus, and they sort of bond together based on their electrons. So that's where you get H2 from. You have the metallic bond, which is where you have two metals, for example. And again, you have to have that positive and negatively charged. And they just kind of meld themselves together. Again, I don't want to go into all the gory detail with chemistry. You're not going to get bogged down with chemistry. You just need to understand in terms of minerals, atoms are what make up minerals. So that's why we're talking about atoms and chemistry right now. So getting back to minerals, there's lots of minerals, tons of minerals in the Earth's crust, and let's face it, out in the universe. Now, in order to tell one mineral from another without being able to look it up, geologists have come up with a series of tests that you can run in order to find some of the physical properties. Things like habit. What habit is the common crystal shape. So going back to the example of table salt, Sodium chloride forms perfect little cubes. Every time, if you could have a big chunk of salt and you just start hitting that thing, it just sort of always has the shape of a cube, and I will get to that in a bit as well. Luster is if I hold a piece of a mineral in my hand, how does the light reflect back to my eyes? Is it look like dirt? Does it look like resin? Then we call it resinous. The first question is it metallic or non-metallic? If it's non-metallic or if it's metallic, it looks like a metal, you're done. It's easy. However, most minerals are non-metals. So they've come up with other descriptive terms to explain what luster is. So things like, does it look like dirt? Does it look like fibers of silk? We call that silky, like with gypsum. Does it look like resin? you know, and then you have the most brilliant of all of the lusters, which is called adamantine, which is what a diamond would be, or what's the other one? Rutile, which is a titanium mineral. They reflect back the most light. That's why women like diamonds, right? They sparkle. That's the whole point of them. Another one here is color. Now, color is very, very misleading. The problem with color is there's some minerals, some of the most common minerals come in every color of the rainbow. For example, quartz, calcite, and fluorite all come in a ton of different colors. You've probably seen those purple crystals, like they call them geodes, where it's all kind of caved out, you know, and it looks like the inside lining is a bunch of purple amethyst. Those are geodes, usually collected in Brazil, but that's all quartz. Quartz is also, there's quartz where you can't see the crystals at all, like tiger's eye quartz. That's a microcrystalline quartz. There's all kinds of colors of quartz. It comes in yellow, which is called citrine. So um, and then calcite's the same way. Calcite comes in almost every color of the rainbow, and so does fluorite. So color is very misleading. There are a few minerals where color does actually play a role because it's a very distinct color. For example, sulfur, right? Sulfur is yellow. There are other yellow minerals, like I said, citrine, calcite comes in yellow as well, and so does fluorite. But sulfur has a very distinct bright yellow color. There's almost no other mineral that I know of that comes in that particular yellow. So sulfur is a very distinctive yellow, and you could use color as a diagnostic feature for that. But most minerals you cannot use color. Now, what streak is if I hold a piece of mineral in my hand, it may look one color in a big chunk of my hand, but if I pulverize it into a powder, it might look completely different. And a perfect example of that is pyrite, or what you might have heard as fool's gold. It's iron sulfide. It has no worth whatsoever other than it's pretty. It makes these cool little gold little cubes, right? If I look at it, excuse me, in my hand, it looks gold. If I scratch it on a piece of unglazed porcelain, it comes off as black. So in its powdered form, it's black. In a big chunk, it looks gold. And there's other minerals that do that as well. Now the problem with streak is there's a lot of minerals that are harder, which we'll get to in a second. They're harder than the streak plate itself, so it's just literally scratching the streak plate. So you don't want that either. And that brings us to hardness, which is the ability to resist scratching. Now, there's a Mohs hardness scale, which you'll see in the book. He developed this sort of relative scale, meaning it has no numbers. There's no numbers on the scale, but there's minerals in there that are sort of the ones that they're all based on. So number one is talc, very soft mineral. You can scratch it with your fingernail. Pretty much, you can scratch it any way you want. Then you have gypsum. Excuse me. Gypsum is number two, which is again very soft. You can scratch it with your fingernail. Then you have calcite, and you go from there all the way up through number nine is corundum, which they use. It's an iron oxide, which they use for things like um, excuse me. They use actually it's not an iron oxide. It's a silicate mineral. Excuse me. No, it is an iron oxide. They use it for sandpaper abrasives like that. And then you have diamond. Now diamond is super hard. So if you were going to assign a number to it and corundum was number 9, diamond would be like number 100. It's way harder than anything else we've ever um, seen on Earth. And then finally, you have cleavage. Okay, now cleavage is the ability for a mineral to break the same way every time you break it. And I'm going to go back to the table salt analogy. I almost gave this away earlier. If you take a big piece of salt, rock salt that you find deep underground, and you just start hitting that thing with a hammer, no matter how you hit it, it comes off in tiny little cubes. If you take your table salt um, and look at it under a microscope, there are these little tiny cubes. That's just how it's called halite. The mineral is called halite. We call it salt, but it's called halite. That's just how it breaks. Now you have muscovite and biotite, which come off in like these flat sheets, right? And you can peel it and peel it and peel it. You can peel it so thin you can see through it, and it feels like plastic, even though it's an actual mineral. It's actually quite fun. So here, oh man, there's a slide for each one of these, and I just talked about all of them. So I'm going to kind of whip through these. That's a metallic luster. That's galena. Now, here on the left, this one here, this one's kind of dull because it's been oxidized. It's been exposed to the air. But if I cut it open, you could see this bright, shiny metallic color. Galena is another mineral that creates those really cool cubes, perfect cubes. Like I mentioned, color is very difficult because fluorite, calcite, and quartz all come in every color of the rainbow. Okay, so you can't use color a whole lot, even though as humans we rely on our eyes quite a bit. So, but color doesn't always work. Streak, like I mentioned, okay, so you can see that there's a gold color in this, and then when I scratch it on this plate, it comes off as black. All right, so the powdered mineral looks different than the solid mineral. The crystal shape, okay, again, that's pyrite, so that's the fool's gold. It comes in these cool striated cubes. You see these lines around here, all these straight lines. Those are called striations, and they're very very cool, cool shapes, you know. And a lot of it, like stuff like this, where it looks like a ball, even with angular faces on them. So pyrite's a pretty neat looking mineral. Here's the Mohs hardness scale. I was close. I said 100 for diamond. It's actually 80. All right. Um, so here's some talc gypsum. See, as you go up the scale here, they get harder and harder. And then here's your fingernails about 2.5, a penny is about 3.5, a wire nail is about 4.5. So these, if you're learning how to do geology, what this is sort of a process of elimination. So if I give you a mineral that you have no idea what it is, if you can scratch it with your fingernail, it's got to be 2.5 or less. If you can't scratch it with your fingernail, it has to be 2.5 or more. Hopefully that makes sense. Then let's say I have a piece of quartz and the quartz actually scratches it. Now you got to make sure you know which one is being scratched. Let's say I take my piece of quartz and I scratch the piece I don't know what it is. Well, that means it has to be more than 2.5 and less than 7. So that's how you kind of whittle it down by using one of these options on the right here or another set of known minerals from a hardness test set. So you scratch, kind of work your way down so you narrow down roughly where the mineral that you have no idea where that would be. So I used to do Cub Scout groups to get their geology badge, so I would have them do this. So it's a process of elimination. Cleavage, and I mentioned this before, mica, or we call it muscovite and biotite, you could peel it really thin. You could see some of these smaller pieces down here. It's just fun. It's the weirdest thing. You could sit there and peel a mineral, and it's so thin it feels like plastic. You could make, many, many years ago, hundreds of years ago, in areas where this stuff is really prevalent, like in parts of California, they would make windows or like fireplace fronts out of this stuff because it's a mineral. It doesn't melt, but it's so thin, it allows the heat and everything to come through, but it didn't melt because it's a mineral. It's very cool stuff. All right. There's some other physical properties, things like fracture. Does it break in random ways? A lot of minerals don't do that. The specific gravity, which is if I hold a piece, I'll use nice round numbers. If I have a pound of talc in one hand and a pound of lead in the other, all right, the lead is going to feel a lot heavier because gravity, it's a very dense mineral. Okay. And then you have the tenacity, which is the resistance to cutting, breaking, bending. Um, that's those, you're not really going to use that too often. I've never used that ever. So you have some other kind of odd things like conchoidal fracture. Um, Both quartz and obsidian do this. You could see this conchoidal is like it means shell shaped sort of, and you could see these sort of rounded. I know my lines aren't very good there. Sorry. These rounded edges. So if you see this and it's black, a piece of black, it's probably obsidian, which is glass. It's just got a lot of uh, bits and pieces in it that make it black, or um, quartz, which is also silica, but it's just more clear. So they both have this thing called conchoidal fracture. There's some other properties, and I'll go through a few of these real quick. Taste. I don't suggest you go taste all your mineral samples, but if you suspect you have salt, it's going to be salty. Smell. If sulfur smells like rotten eggs, I actually read in a book that if you take arsenic minerals, please don't do that. The arsenic is bad. It's very highly poisonous to humans. But if you take an arsenic mineral and hit it with a hammer, it smells like garlic. I've never done that. Don't do that. Is it elastic, malleable? Malleable means you can pound it really thin. Gold is a perfect example of that. Gold leaf, you can take gold and pound it very thin. It's a very like you can shape it. Is it magnetic? How does it feel? And then reaction with hydrochloric acid. That's more of a test to see if it has the carbon, if it's a carbonate mineral. So if you remember, ever doing, maybe you did this where you made the homemade volcano with baking soda and vinegar. That's a reaction of an acid and a carbonate. And, the baking soda is a carbonate, so it forms all those bubbles. That's what hydrochloric acid does to carbonate minerals. Now you have mineral groups, right? There's only a few dozen of those, but by far the most common mineral group is the silicates. I mean, it's the most of the Earth's crust is made up of silicate minerals. So of all of the elements, now these are elements, not minerals per se. Of all the elements, these are the ones that you're going to find most often in the minerals that they make up. Oxygen is huge. Silicon is the biggest. Aluminum, iron, calcium, sodium, potassium, and magnesium. These are these and a combination of a few others are the building blocks of all the minerals on Earth, pretty much within the Earth's crust. That is. So most of the minerals you're going to see have one or more of these elements in them. So here's the bulk of the Earth's crust, and by far the most is oxygen, right? And then next is silicon, and that's what makes the silicate rocks the most abundant in Earth's crust, is because they're the most abundant elements. They form very easily together, hence you get a lot of silicate minerals. Then you get things like iron to a lesser degree, aluminum, sodium, magnesium. So you get the idea. So when we talk about rare earth elements, like things like platinum, see only 1.5% right here, 1.5% of the entire Earth's crust is made up of something other than these big ones. And think about that. So I saw this in a website somewhere where, some of those rare earth elements, you're talking like 0.00000000001% chance of finding it in the Earth's crust. It's crazy small. Now, the rock forming mineral groups are things like the silica oxygen tetrahedron, sorry. So, in order for silica to bond with oxygen, it requires 4 oxygen to 1 silica to make everything balanced. Okay. And then once you have that, it combines with other elements. That's a very, very balanced equation chemically. So the SiO4 thing here, all right. And what you need to understand is this is the most common grouping in the Earth's crust, but then you can combine that with other minerals as well to create other silicate minerals. So the groups are based on their chemical structure. And again, I'm not going to go into gory detail about this, but you have things like olivines, which are typically formed very deep under the earth, the pyroxene groups, which are sort of the chain, and then you have the double chains, which are the amphibole groups. And again, we'll see examples of these as we go, but just understand the silicate minerals by far dominate what you're going to find in Earth's crust. They're not necessarily the prettiest or most noteworthy minerals, but that's what you're going to find most of the time. So here's an amphibole. It's typically a pretty dark mineral. It's got a lot of magnesium in it, and which helps make it dark, along with aluminum and stuff like that. That's the dark one of the dark minerals from that can be found in certain granites. So you have micas and feldspars. Micas are the sheets that you can peel off, like biotite, which is the darker of the two version, and muscovite, which is the lighter of the two version. Again, you've seen mica before. If you've seen granite, you've seen mica. It's in most granites. Um, and then you have feldspars, which are typically either white, clear, or pink. All right. And that pink is what makes up red granite. We call it pink, but it's, the red granites. Um, and that's a pink feldspar that creates that particular color. Um, the feldspars are the most abundant group by far in the Earth's crust, and they all have quartz in them as well. Again, hopefully you can understand there's a common theme here. Most of the rocks you're going to see are silicate rocks or silicate minerals. So here's a potassium feldspar. Um, one's called orthoclase, or they're both called orthoclase. All right. Now this is sort of the whiter version. And you have here's a type of quartz. This is the pink variety. Now, when you see pure quartz is pure quartz. It's clear. It's just silica and oxygen. It's glass essentially. There's these things called Herkimer diamonds, named for the town they were first discovered in Herkimer, New York. They look like diamonds. They absolutely look like diamonds. We have a little display of them in our museum at UWM, but they're not worth anything. It's just very, very clear quartz. That's what it is. So you do have non-silicate groups found in Earth's crust, but these are much more rare. But these are actually easier to understand chemically because they're kind of binary. You have like one of this and one of that. So things like the oxide. So iron oxide is where we get iron from. All right. And that's what they mine out of the ground to get iron. You have the sulfides, which like pyrite is lead sulfide. You have carbonate minerals, which have CO3, um, which is the ones that bubble under acid. All right. You have halides, which are salts, like sodium chloride. And then you have native elements that are both elements and minerals, things like pure iron, silver, gold, platinum, things like that. Those are elements and minerals. They are found in rocks. So they're kind of both. They're just a very pure, think of it as a sort of a pure mineral because there's only one type of atom present. So if you have a piece of gold, that's the only atom there. It's not combined with anything else. If you have a piece of silver, platinum, or something like that, that's all there is there. There's nothing combined. When you start combining things, then you get things like bronze or you get alloys. But a native element is one kind and one kind only of that particular atom. So here's some of the common non-silicate mineral groups, and you could see some of these. Hematite is the one that I couldn't remember the name of. Hematite is an iron oxide. That's the one where we get a lot of the iron that is used for steel making purposes. Um, One of the things I try to stress to like kids that come through my museum when I do tours is a lot of these minerals are pretty cool looking. Some are ugly. Um, like bauxite. Bauxite is the prominent ore that we get aluminum from. We think aluminum cans are these shiny cans, right? Bauxite is its dull, ugly mineral, but that's where we get aluminum from. Um, you have halides. You could see, look at the economic use column there. Try to understand that there's a reason why we have these things. They're used for stuff. I mean, iron's used for steel making. Without steel, you don't have buildings, you don't have cars, you don't, I mean, it's the infrastructure of everything. Bridges, rebar is made out of steel. So you have to have steel, or my favorite, my cast iron pan that I make food in. So you have to have all this stuff in order to make make the world go round, so to speak. Some of them are better than others. You don't want to mess with things like mercury, but mercury is used for things, just not the same things. Like we don't use mercury thermometers anymore because mercury is highly toxic. It's one of the most toxic substances you can put in the human body because once it's in there, you can't get it out. So just take a look and if nothing else with the chemistry part, look into what things are used for because you get a better appreciation as to why they're mining molybdenum or why they're mining neodymium or whatever weird element you can think of. And again, a lot of it's used for electronics and stuff like that or steel making. So it's kind of interesting. So you have for the non-silicate minerals, you have carbonates are a huge rock forming group as well. Limestone and marble. Hopefully you've heard of both of those. We have marble halls and walls and marble is a very hard what we call metamorphic version of limestone. We'll get to metamorphism in the next chapter. But limestone is made up of carbonate mineral. It's like pure carbonate. Um, and that's the stuff where if you put acid on it, it bubbles. That's how you could test. So a lot of these things have economic value. Obviously, people want marble countertops or nowadays granite countertops, things like that. So all of these are natural resources, right? And we have to mine them out. I'm not going to go into this in gory detail, but there is an element, no pun intended, an element of this that you always have to remember is that these are non-renewable sources. So as we extract things out of the ground, things like copper and all that, and I'm a geologist, so there's an old term that says if you can't grow it, you have to mine it. And that's pretty true. All right. We've gotten better at recycling certain things like aluminum, all right, aluminum cans, stuff like that. But a lot of the resources that are in the Earth's crust, things like oil and gas and coal, and then a lot of the precious metals, once they're taken out, they can't get put back in. Their grow rate is way longer than our human lifespans. I mean, it takes millions of years to create oil. It takes millions of years to create gold. All right. So we have to be mindful of trying to not extract more than we need. And it's easier said than done, right? But because there's a huge need for things, especially like with electronics and stuff like that. So I just want to bring that up a little bit here. There are lots of renewable resources as well, things like wind, water, sunlight. So that gets into the energy portion of it and everything like that. Oops, excuse me. Um, we will eventually extract these minerals, and the thing is that they could be mined for profit, and when there's no longer profit, they're going to not be mined. It's a market value just like anything else, even seafood, right? You go to Red Lobster or whatever and it says lobster is at market price. So it's wherever the market is, and gold has been worth a lot lately, and platinum obviously is worth a lot. So eh, where the market is will determine how much they take out of the earth. The same thing applies with gasoline prices, right? When oil is high, when oil is high, business is good. They hire people. They go find more oil. When the market's low and gas is cheap, they start laying off people. It's all market driven. All right. So you got to keep this in mind when you're talking about non-renewable resources. So I'm going to leave you with this last picture. This is the largest open pit mine, I believe, in the world, which is in Utah. Go look at this on Google Earth. It's pretty cool. The Binghamton mine, I think it's called. I can't remember what it's called. It's one of the largest open pit mines in the world. It's a copper mine out in Utah. It's it's beautiful in the sense that it's so big that it's hard not to like wow. But at the same time, that's a huge human scar as well, right? So, I mean, it was probably more beautiful before the mine got there. That one mine accounts for a ton of the U.S.'s copper. It's I think 15% or something. That mine has just been extremely profitable. Um, so, but unfortunately, there's both economic and environmental issues that go with it. So, well, I hope these are going to help you. Um, I'm going to try to do as much of this as I can. Again, the other course that I got handed, uh, unfortunately, I have to make everything from scratch. So I'm just going to use these slides as a springboard and just talk about them. And it's fun for me because I don't get to talk about geology much anymore because of the nature of what I teach. So this is kind of fun for me too. It'll be a nice review of some of the stuff I haven't talked about. If you have questions, please feel free to ask me, via email or whatever. I'm going to post these up on the Blackboard site and you'll be able to watch them right there. You don't have to go to YouTube or anything like that. Blackboard's nice that way. It allows me to upload them. So there we go. The next chapter will be chapter, oh, I forgot what chapter this is. This is chapter 2. I think chapter 3 is about rocks. So this, again, going back, this chapter is about the building blocks, sort of the ingredients that make up rocks. And then the next chapter will be talking about the rocks themselves, how they form and things like that. Igneous, sedimentary, metamorphic rocks. So, all right, I hope these help you, and we'll see you soon.